This is Maths Linear Algebra Tutorial 8, Question 7, Part 21. We are asked to answer true false for the following questions, 21a to 21d. We are also asked to justify each answer. The following information are given to us. The matrices A, B, P, D are square matrices n by n. The following information is given. A is diagonalizable, and if A equals to PDP minus 1 for some matrix D, an invertible matrix P, is this theorem or is this statement true or false? Actually, in the first glance, you have think that it is true, but the correct answer is false. The reason is false is that the only information about D given to us is some matrix. It should be a diagonal matrix for diagonalization theorem. In addition to that, P must be invertible. Let us see where this information is given in our slide. It is 8.1.5, page number 6, theorem number 5.2.1. Let's go to this page now. In diagonalizing a matrix, when the matrix given to us is an n by n matrix, A is diagonalizable if it has n independent eigenvectors, and in addition to that, the matrix D must be a diagonal matrix, in addition to P being an invertible matrix. So this information is found in this slide 8.1.5, page number 6. We now turn our attention to the second question. Let's read the question. If Rn has a basis of eigenvectors, then A is diagonalizable. So first, he tells us that we are in the space of Rn. And the little n here is the same n as the n by n square matrix. What is a basis? A basis means independent vectors that spans the space. And the space we are interested in is Rn. So to get an independent set of vectors, we need n of them. So if we have n independent eigenvectors, then A is diagonalizable, because this was what was the theorem stating anyway. 8.1.5, the same page number 6, and theorem 5.2.1. Let's go there again. This is the theorem. It must have n independent, linearly independent eigenvectors for an n by n matrix. This statement is equivalent to the question which requires us to have a basis for Rn, which is this question here. Alright, now we'll turn our attention to the next part, 21c. In 21c, we are given that A is diagonalizable, and the condition, whether it's true or not, is if and only if A has n eigenvalues, counting multiplicities. And in this case, the answer is false. What it needs is to have n independent eigenvectors. It does not. In fact, you will always have n eigenvalues. Let's go to the slide 8.1.3, slide page number 10, to see one explanation why this answer is false. Here, the algebraic multiplicity, meaning the number of eigenvalues, will always be equals to n. The geometric multiplicity, counting how many eigenvectors are there, may be less or equals to n. It is the geometric multiplicity that is important. If we can have this to be true, geometric multiplicity equals to algebraic multiplicity for all I, then the matrix is diagonalizable. We now turn to attention to 21D. The statement says if A is diagonalizable, then it is invertible. The answer is false. The reason is that invertibility only requires the eigenvalue to be not equals to 0. But diagonalization, you can have, all you need is to have a complete set of eigenvectors. The eigenvalue can be 0. So this concludes question 721A to D. Thank you.